Yes, indeed. Thank you very much. Good morning, everyone, and thank you to the organizers for setting up this meeting in such a beautiful location. I am, in fact, going to talk about binaries, and there's several things that I want to be able to do here. The first one is I want to give you kind of an overview of what binaries involving stellar mass black holes can do in the center of a galaxy. There are a variety of processes that they may undergo, and as I hope to demonstrate, this makes them interesting prospects both for LISA successors and also for LIGO and Virgo type ground-based detectors for gravitational waves. I will then tell you about two papers that my collaborators and I submitted over the summer, one with Pau, one without Pau. The first being tidal disruption of a tidally separated binary, the second being an indication of what happens when binaries fail you. And if there is time at the end, I may talk about a couple of other effects, but we will see. There are multiple things that can happen to a binary when it is in the center of a galaxy where, as Tal indicated a couple of days ago, near the centers, the number density of stars can be maybe 10 to the 8 per cubic parsec, or 1 billion times what it is in the solar vicinity. Now, during this period, in the interactions that can occur, these binaries can sink due to two-body relaxation. If they contain a black hole, they are more massive than the average object, so they would tend to sink. Tal had focused on resonant relaxation and the change in eccentricity that you can get, if not the semi-major axis. You can also have considerable evolution via three-body interactions, where the binary interacts with a third object, which we call an interloper. And this can change the internal properties of the binary, like the semi-major axis or eccentricity, possibly leading to situations where the binary will merge with itself and provide a ground-based gravitational wave source. It can undergo a long-term secular effect called Kozai oscillations, or the Kozai resonance, which has received considerable attention in this community over the past decade or so for reasons that I hope to explain. And it could be tidally separated by the supermassive black hole, which presumably exists in the centers of most galaxies. So we'll go through these bit by bit to try to understand a few of these processes, and then we'll talk about those two applications that I mentioned. Now, as I said, a black hole by itself, or therefore in a binary, is more massive than the average star. If we take 10 solar masses as a rough value for the mass of the black hole, the average star might be 0.4 or 0.3 solar masses, so clearly the black hole is considerably more massive. It therefore undergoes dynamical friction on a time scale, which is the relaxation time scale. So I have the formula up here, somewhat rounded, where you have a variety of quantities. This log lambda is the Coulomb logarithm, and since all logarithms are 10 to within a factor of 2, you might as well take it to be 10. This sigma is the velocity dispersion in the region where the object is. So this could be tens to hundreds of kilometers per second in the galactic center. This big G is constant. Rho is the mass density on average of the stars in the vicinity of this object. Note that, therefore, only the density matters, not the individual masses, as long as those individual masses are significantly less than the mass little m of your binary, which is 10 or 20 solar masses in our case. However, as Tal indicated, even though this is the time scale on which the energy relaxes, so on the time scale on which the semi-major axis might double or halve in this case, it is the angular momentum relaxation that can be much faster. Reasonable enough, if you have something with a very high eccentricity, even a slight little tweak at apocenter can change the pericenter and therefore the angular momentum considerably. And so that is this expression, or E is the eccentricity. And a rough answer about how long these take is that for a 10 solar mass object, so your binary here, the energy relaxation time is less than a Hubble time, as long as your central supermassive black hole is less than about 10 to the 7 solar masses. So Milky Way-ish type galaxies could have black holes relax and sink considerably into their centers. Now, Tal discussed resonant relaxation at length, so I won't go over this much, but I will mention that, again, the issue is that if you have a circumstance in which the orbits of individual stars trace over themselves many times, you can act as if their mass is spread over a wire, weighted by how long it spends at each portion of its orbit. Now this is going to occur if two things happen. One is that the objects of interest are close enough to the supermassive black hole that the black hole potential dominates as opposed to the collective potential of the other stars, but not so close that general relativistic precession comes in. This is the Schwarzschild barrier that Tal discussed. So this is something that, because you're integrating over many, many orbits, you have a time stationarity, which therefore corresponds to energy conservation. You cannot change the semi-major axis of the orbits as a result, but you can change the eccentricity. Here I have some of the original figures from the original paper suggesting resonant relaxation. I recommend you read this paper if you wish. It's a nice description. And essentially what these figures demonstrate is that whereas the energy of the orbit, or its semi-major axis, undergoes a random walk with time, over a much longer time scale than the step size of that random walk, the angular momentum, either scalar or vector, will change linearly. And Tal, of course, gave much more description about this. Three-body interactions are also extremely important to understand how binaries evolve. Now, what we know is that if you have three comparable mass objects within the same near vicinity of each other, their interaction is chaotic. This means that it is not possible to have some sort of analytic situation where you write down the initial conditions and you know what the final condition will be. People have therefore, since the mid-1970s, done a very large number of computer simulations to find trends. One important trend is that when you have one of these interactions, some binary and some other object or interloper coming in, then the final binary you get after all is said and done tends to be composed of the two most massive of the original three objects. One consequence of this is that even if you have a black hole that is born single, it is fairly likely to swap into a binary at some point in its life. So we don't have to rely on the black holes being born into binaries. Another tendency has to do with whether the binary at the end is tighter than it was, or or harder, that is, or whether it's softer, i.e. wider. And the tendency, again, is that hard binaries harden, soft binaries soften. Now, the definition of a hard or soft binary here is related to the overall energy of the system. So you've got our negative binding energy, we've got a positive kinetic energy. If the total energy is negative, so that is to say the potential energy here is greater in magnitude than the kinetic energy, then the tendency is what I've actually shown in this cartoon, where you end up with a tighter binary than you had to begin with. Now, this is a purely Newtonian process. There are GR corrections which you can add in strong gravity, but also notice that this is something that, in the Newtonian limit, conserves energy, so it has to go somewhere, and that somewhere is into the recoil of these objects. So we'll come to that later. Now, the issue is that if you have a hard binary and it hardens, it's smaller, so its cross-section is less for these close interactions. On the other hand, if you soften a binary, then its cross-section is larger and even softer, so it tends to soften further. So softening tends to be a runaway process, whereas hardening is not. Now, one consequence of this is that you can make an estimate about the likely outcome for a stellar mass black hole in a binary as it sinks in the galactic center. Far out, where the velocity dispersion is maybe not that large, the binary may be hard, and so the interactions will tend to harden it. However, this interaction is not something that is going to interact with a large amount of mass. Characteristically, you need to interact with roughly the mass of the binary in order to harden it by a factor of 2 or something like this. And my student Vanessa Wahlberg showed in her thesis that if you compare this with the relaxation time in the system, it is typically the case that the relaxation time is less than the hardening time, about a factor of 2 or so. So one of the possible consequences is that when you take this binary, it might harden a little bit as it sinks, but it'll sink until the velocity dispersion, which of course increases as you get closer to the supermassive black hole, is high enough that the interactions are now softening interactions, at which point it could be softened to the extent that it actually separates or ionizes. This is not a guarantee. There are many other things that can happen. One of those things, which is potentially of interest to ground-based gravitational wave detectors, has to do with the process of Kozai resonance, or Kozai oscillations. Now, Kozai himself was a planetary dynamicist, and in about 1960, he noticed, as others had as well, that there were very few short-period comets which had a high inclination to the ecliptic. He modeled this, as any good dynamicist would to begin with, as a restricted three-body system. You have the very massive Sun, the much less massive Jupiter, and the effectively massless comet, and demonstrated that here you have a secular effect where over many orbits of the comet and Jupiter, therefore averaging over these, because of the averaging, again, you do not change the energy of the comet's orbit. You do not change, therefore, its semi-major axis. But what you do change is the inclination of the orbit, while conserving the z angular momentum along the ecliptic in this case. So if the comet starts out at a high inclination, it goes down to a low angle where it conserves that angular momentum without changing its semi-major axis. Net result is the eccentricity goes way up. So the short period comets exist, and in fact we see them in SOHO, but they are destroyed by the sun. They get to a high enough eccentricity, they just hit the sun. So in principle, in certain interactions, you can imagine that our black hole binary would go through Kozai oscillations, get to very high eccentricity, and possibly merge, because at high eccentricity you have a small pericenter. However, something that Doug Hamilton and I showed in 2002 is that when you add the first post-Newtonian term, the precession term, this limits the eccentricity you can achieve. Essentially, this is because the process of the Kozai resonance is one in which you have to maintain certain phase relations between angles. And the reason that it goes through cycles, bouncing at, in the classic case, an angle of about 40 degrees, is that when you get to that point, the precession rate is such that it can't keep up, and therefore it reverses and goes back. Thus, any source of precession is going to limit the efficacy of the Kozai resonance in getting to very high eccentricity. As an example, again, in our solar system, you know that Uranus is tipped by 97 degrees relative to its orbital plane. It has moons around its own equator. If Uranus were not rotating, it would not have those moons there, because Kozai with the sun would cause those moons to go to high eccentricity and plunge into Uranus. Uranus is, however, oblate. This produces a precession term which offsets Kozai. Similarly, general relativistic precession can do the same thing. Not kill it completely, but at least limit the maximum eccentricity. And what you find when you do these sorts of integrations, as Lin-Ching Wen did following our paper, is that you're not likely to get a palpable eccentricity in ground-based interferometer bands. But this is something that could potentially have a significant effect. In our case, when we're talking about the galactic center, Antonini et al. Pointed out last year that in these galactic centers, you after all have your binary and a supermassive black hole. And that this could act as a triple system and possibly lead to large periodic oscillations in the internal binary eccentricity and inclination. So it's conceivable that even when you include the GR precession effect, this could lead to close enough pericenter interactions that it could boost the rate of mergers significantly. So this is an interesting source for LIGO and Virgo events to consider. And my student Siddharth Kumar is currently studying these with some Monte Carlo simulations. Now, the last basic effect I'll describe before talking about what I did on my summer vacation is tidal separation. If your binary gets too close to the supermassive black hole, then it can be tidally separated by the supermassive black hole. Now, the way that this works is if you imagine having your binary plunging on a reasonably close orbit to the black hole, then one of the objects will be captured and the other will be flung out at high speed. Indeed, this is the leading candidate to explain the so-called hypervelocity stars that we see in our galaxy right now. young stars that are moving much faster than they should. It's thought these have been produced by tidal separation from our own supermassive black hole. Now this leads to properties of the orbits that are a bit different from what you might expect from a standard extreme mass ratio in-spiral. A standard emery is one where you have a single object coming so close that it actually loses energy to gravitational radiation and then is able to spiral in over hundreds of thousands or possibly many more orbits. In this case, however, for the binary tidal separation, you do not need to lose energy to anything. Energy is conserved. So this means the critical pericenter is much larger than it would be for a standard emery. So although the fraction of binaries is low compared to the fraction of singles, it is possible that the increased cross-section of this effect might be able to balance. This would give you different orbits as well. I mentioned the higher pericenter than in the classic emery case. You also have a smaller apocenter. So its dynamical evolution is different than one might have thought for the standard emery. It's also been pointed out that because you can come in therefore from a fairly large distance, triaxiality in the galactic center region might be able to boost these rates more than they're likely to for standard emeries, whose rates are dominated well inside the supermassive black hole's radius of influence, where it enforces a near sphericity of the potential. So now let me talk about the Pau-friendly paper that was submitted this summer. And this involves tidal disruption. And we heard a bit about this from Nick Stone yesterday. The standard picture of this, which I'll elaborate on a little bit, is that you have a single star, which happens to come in a very high eccentricity orbit, like a standard emery, if you will, and that this is tidally disrupted, and as I'll give you a quick derivation, you come up with a characteristic mass fallback rate of 10 to the minus 5/3. What we proposed in our paper is that there's the possibility that you'll have a tidal separation of a binary where the remaining object is not tidally disrupted until possibly long thereafter, where dynamical processes eventually bring it close. If this happens, it's possible that this occurs from a much lower eccentricity orbit, which, based on work that had been done about 20 years ago, will tend to give you a shallower decay for a different reason. So to understand this, let's go back to the issue of the standard high eccentricity disruption, parallel to the standard emery. So here we have our single object, our single doomed star, which goes very close to the supermassive black hole. Now for a standard like 1 solar mass star, a 10 to the 6 solar mass black hole, it would need to get to maybe 0.6 AU to be tidally disrupted. And of course it could come closer in some cases. So it would get ripped apart, and the analyses that have been done, numerical and analytic, indicate that about half of the mass is thrown away immediately to infinity, and then of the remaining bit, about another half of it, so remaining only a quarter, is possibly eliminated by shocks as the various streams intersect. So you get something like 20%, give or take, of the original mass in your orbit. Now, in terms of this characteristic decay, the original analysis of Martin Rees, when corrected for an error that he made, it can be phrased in this kind of fashion. This particular derivation is from a paper by Lodato et al. In 2009. Essentially, you say if you have an orbital period of t, then you can relate that to the specific energy of the orbit of the debris as it's raining back by this formula. So, even though you're going to have some material thrown away, you'll have energies all over the place. The positive energy being thrown away, the zero just barely bound, and then all energies in between. You can ask, what is the accretion rate or the fallback rate from the stream that comes back? So we just do our standard calculus thing and write it like this, and you notice that there's a t to the minus 5/3 here, and some constants. So, if you make what is a standard simplifying assumption that the amount of mass in any given energy bin in the entire fallback stream is constant, then in fact you get your t to the minus 5/3. Now looking at this, you may say, why would we say this? Well, it's a simple assumption. And it has been pointed out, of course, that it may not be completely true. That same Lodato et al. Paper, 2009, pointed out that the mass fallback rate could in fact differ from the minus 5/3 level, depending on the structure of the star. It has also been pointed out that, of course, we do not look at mass fallback rate when we're doing our observations. What we see is the flux in some energy band. And was pointed out the following year by Lodato and Elena Rossi that this is not something which is going to be expected in all cases either. And it depends very much on where your accretion disk is in its emission compared to the band you're looking at. If, for example, your entire accretion disk is emitting at temperatures and energies characteristically above what you are looking at, then you're going to get a flatter law. If it's all less, then you're going to get a steeper law. Nonetheless, when you actually work it out, and these people did in some detail, you find that the minus 5/3 is remarkably good for a whole lot of a typical disruption in, say, X-rays or later on in optical. So it's not a bad approximation, even though it seems like it should be a bad approximation. So let's now go to the picture that Pau and Gareth Kennedy and I proposed this summer. Going back to the tidal separation. So what we recall is that if we have our binary tidally separated, leaving one of the two in a more tightly bound orbit around a supermassive black hole, then this remaining object, if its pericenter is well above the tidal separation, will evolve by a combination of two-body relaxation and gravitational radiation. The typical distances we're talking about here are inside Thales' Schwarzschild barrier, and so resonant relaxation is likely to be ineffective, in our opinion. If the eccentricity is low at the point of disruption, then the time evolution is different. So just as a quick look ahead, in the standard case, it's fallback that dominates the accretion rate. In this, it's the self-similar evolution of a remnant disk that dominates the rate. So it's a different process. But we have to think about what are the circumstances in which you're going to expect a disruption from a low eccentricity orbit. So there's this competition between two-body relaxation and gravitational wave circularization. Now, two-body relaxation could increase or decrease the eccentricity, and therefore it could change in either direction the pericenter of the orbit. But if the pericenter goes up, nothing happens. So we're only interested in the case when the pericenter goes down. And if it goes down enough, then you might be able to get a tidal disruption that looks like the normal. Typically, the initial state is that the remaining object after tidal separation has an eccentricity of about 0.98. So because this eccentricity is so high, angular momentum relaxation is a lot faster than energy relaxation, so that's all we're really needing to consider in this case. To compete with this, gravitational waves circularize orbits, especially very high eccentricity ones like this. So the question is, which wins? And what we find is that for the typical semi-major axes that Pau and Gareth found in their simulations, and scaling by a 10 to the 6th solar mass black hole, we're talking about a critical pericenter of about 0.6 AU, meaning that since gravitational radiation has a steeper radial dependence than the relaxation, the two-body relaxation, below this pericenter, gravitational waves dominate the evolution. Above it, two-body relaxation does. So if the disruption occurs at a pericenter distance less than this, you are going to tend to circularize. If it's more than that, you're going to tend to have a fairly eccentric orbit. We can compare this with the disruption radius of a main sequence star of some mass m, which we scale to solar masses. We find it's about the same for 10 to the 6 solar masses. So we look, however, at the dependencies on the mass, and we see it's much stronger for this critical pericenter. As a result, if your mass is at least a few times 10 to the 6 solar masses, you would have a tendency to circularization. Now, there will also be tidal effects going on at the same time, which would have to be examined in more detail at some later point, but there will tend to be circularization. So for masses of at least a few million solar masses, this is where you might have enough circularization that eventual tidal disruption is different from the standard case. Now, if you do end up with a relatively low eccentricity, your next question is, what's really going to happen? You could, for example, imagine that if the orbit circularizes enough, then by the time the star got to the tidal radius, it would be able to undergo steady mass transfer. And this steady mass transfer, if it happened, would be at a very low rate based on the gravitational wave timescale, which is what would drive the evolution. And this would be maybe less than or about 10 to the 41 ergs per second and steady, not distinguishable from the standard low luminosity AGN. But it's actually not easy to get to that low in eccentricity. What you find is that if you have an orbit of some eccentricity E at the tidal radius, then the amount of energy that you need to dissipate in order to circularize is of this order. So E squared times the 2/3 power of the ratio of the mass of the central object to the mass of your star. So this ratio is about 10 to the 6. So as long as the eccentricity is more than about 0.01, then you're going to find that the dissipation is by gravitational waves is insufficient to circularize it enough. Now there's always a competition, again, between things like tidal dissipation and gravitational wave dissipation. And you might also wonder whether the energy that is dissipated could be dissipated slowly enough that the star could simply radiate it. However, we find that for typical circumstances and for tidal Q factors in a reasonable range of 10 to the 5 to 6, that disruption is more likely than steady accretion. And in addition, when the tidal energy is deposited much faster than the Kelvin-Helmholtz time, so the star is not going to be able to radiate that energy. It will, in fact, have all the energy deposited, and then something bad will happen to the star. Now, there's a very great amount of confusion about exactly where the tidal energy would be dissipated. For example, is it dissipated everywhere in the star equally with mass? If so, then maybe the star would homologously expand and entirely disrupt, and then you have the entire mass of the star, and it would disrupt in a way that is following the remnant disk loss found by Knitzel et al. So rather than t to the minus 5/3, it's a shallower law. Okay? The other possibility, or another possibility, is that maybe most of the tidal energy is deposited into the envelope of the star, in which case the envelope will form your disk, and the core will be a nice little emerald. Now, as far as distinguishing these from your standard tidal disruption t to the minus 5/3, it has to be said that when you look at the roughly 10 events that Nick mentioned, rarely has an event been followed with sufficient time fidelity, and doing so with enough measurements, to say that it's definitely a t to the minus 5/3 power law or something like that. The Swift event, the most recent one, there have been some claims that it's a really good candidate, but it's difficult. Nonetheless, it is possible that you would have a separate type of power law, and it's also possible that you would be able to get a gravitational wave and electromagnetic event going on. Now, I want to tell you about the other thing I did at my summer vacation, and this is when binaries fail you. Fail you in the sense that, as I'll describe, they are normally a source of energy in dense stellar systems which can hold it up against core collapse. But we think there are some situations in which this may not operate. This is work with Melvin Davis and Jillian Bellavary, who is a very good postdoc at the University of Michigan. And essentially what we're saying is that in the relatively high redshift universe, Z10 to 15, there may be nuclear star clusters, and because of hierarchical merging, a lot of gas can be flowing into these regions. And if this happens, it could contract the cluster and lead to runaway mergers. So to describe this in some more detail, let's begin with our starting point, which is nuclear star clusters. Now, we know these exist. Here's a lovely little picture of our very own Milky Way's nuclear star cluster. And let's say that, as is consistent with some n-body simulations, we have similar nuclear star clusters in the redshift squiggle 15 universe. These are total mass maybe 10 to the 7 objects, solar masses, radii of a few parsecs, which therefore would have velocity dispersions of maybe 30 kilometers per second. This is therefore not the population 3 scenario. You've got a lot of stars that are formed, so you are already, therefore, into the second generation of stars. Now, simulations that have been done by a variety of people, including Julian, who produced the figure and the simulations going with it, in this early universe, unsurprisingly, there's a whole lot of gas. It hasn't all turned into stars. And because of this, when you have hierarchical merging, a lot of gas is flowing in. And indeed, at the relatively early time, so 15 or something like this, when you have these inflow episodes, the gas mass can be significantly larger than the stellar mass. Now, there's a picture that has been proposed, and with a lot of calculations, by Lucio Meyer and colleagues. And what they find is that when you have a lot of gas, like much more mass and gas than stars, that the self-gravitating nature of the gas leads to the bars within bars instability of angular momentum transport. And they find that most of the gas can actually be funneled well into the center of the cluster. So they actually find the gas going all the way into inside a 1/10 of a parsec, which is their resolution limit. So if we adopt this particular picture so that the gas can actually flow very close in, then because the cluster is now much more massive than it was, if the orbits conserve angular momentum, which seems reasonable, you find that the velocity dispersion is actually increased by the mass factor, so the new mass divided by the old mass. So the radius contracts and the mass goes up, and the velocity dispersion could increase by a factor of about 10 in some circumstances. So this is where our failure of binaries comes in. When you think about a stellar cluster such as a globular cluster, or presumably these nuclear star clusters if they did not originally have supermassive black holes, you find that the tendency, without anything else stopping it, would be for the center of the cluster to contract and for the exterior to expand. This turns out to be part of the beautiful thermodynamic analogy that exists for clusters. It is cognate to entropy increase. Now, if nothing else stopped it, at the central regions, as they get dense enough, at some point their evolution time becomes shorter than that of the exterior, and so they lose thermal contact, and theoretically could actually go into core collapse, which we'll describe in a second. But what stops this in globular clusters, if you don't have a massive black hole, is binaries. You recall that when we discussed 3-body interactions, I said that you can have a tightening of a binary, but the energy has to go into recoil. So these binaries, whose total binding energy can be considerably greater than that of the entire cluster if you have tight binaries, can actually keep the cluster from core collapse. So they just act as a heating source in the center. But we're thinking about a case where the velocity dispersion has gone way up. So the binaries that were heating the cluster beforehand all had to be hard binaries. Recall, soft binaries soften and ionize. Now, you've increased the velocity dispersion a lot. Doing this means that binaries that were hard are now soft. The softening of the binary actually takes energy away and causes the cluster to shrink a little bit. More seriously is that the ones that are hard now in this new regime are not, in fact, going to be able to stay as binaries for very long. We find that if the boundary between hard and soft binaries is roughly 1 AU, so 30 kilometers a second for main sequence stars, maybe 100 for stellar mass black holes, then binaries cannot hold off core collapse. Essentially, the binaries will interact, but they'll go through various configurations of occasionally high eccentricity, they'll collide and destroy themselves, black holes will spiral into each other. So, above this kind of separation, it seemed extremely difficult to keep your binaries going. As an aside, I think this might be interesting in terms of the formation of black holes at any environment. Essentially, if you have a high enough velocity dispersion, you can't prevent core collapse. Now, when core collapse does happen, work about 30 years ago by Cone, nice simulations, demonstrate that in a finite time, you lead to a density profile that goes all the way to the center. It goes like the number density is proportional to radius to the minus 2.2. Well, this means that at the center, you end up with a very high density indeed. Now, you need a really, really high density for the effects of interest to us to occur. For example, if you go to Quinlan and Shapiro from 1989, they have an expression for the amount of time needed for two black holes to capture each other. If they originally have some relative speed and they come together in a hyperbolic orbit, but close enough, they spiral into each other, then it's this expression. So this is a little bit less than 1 million years for the normalization, but the number density is normalized to 10 to the 12 per cubic parsec. And this is for a reduced mass of 10 solar masses, total of 100 solar masses, and related to the initial speed of 500 kilometers per second. Now, 10 to the 12 is not accessible if you have binaries heating the system. But if the binaries are out of the way and core collapse commences, in principle you can get to these densities. Not only that, but if you have one of our typical 300 kilometer per second velocity dispersions, you can just use Kepler's laws to figure out how much mass that includes at densities greater than the densities needed. It's a lot. It's a few times 10 to the 4 solar masses for these systems. This means that the collapse can occur, black holes can capture each other, and they can rapidly build massive black hole seeds. Now, this is particularly true because the capture rate scales as the total mass to the 12/7, not linearly. As a result, this is what you would call oligarchic growth. There's an initial power struggle between the black holes, and then the lucky one that happens to be more massive than the others is more likely to do the next capture. So it runs away and becomes an extremely massive seed. Now, in addition to that, once you've developed this very high mass, since the cross-section is now significantly larger than it was, it's very possible that it would be able to accrete neutron stars, or even, as Nick mentioned, once it gets past a couple times 10 to the 5 solar masses, it can swallow white dwarfs whole in favorable circumstances. Now, the reason this is of interest to get to a few 10 to the 5 solar masses is if you think about the observations we have of quasars at redshifts of 6+, these are billion solar mass objects, and if you were to take a stellar mass black hole seed and grow it at the Eddington rate for relatively low efficiency and therefore high accretion rate, it would take all of 600 million years to get there. There are a lot of problems with this. Why should it be accreting at Eddington the entire time? Why should it remain low efficiency instead of speeding up? Well, this is one way of dealing with it. Eddington growth is an exponential process. And because it's an exponential process, this going halfway to 10 to the 9, more or less, means that you have the required time to 10 to the 9 solar masses. So this is our suggestion for one of the ways in which you might get these very early seeds and give it a head start on quasarhood. Now, something else to mention, just as an aside, is the role of kicks. And we've heard a reasonable amount about kicks in this workshop, and the question you might have is, isn't it possible that some of those black hole mergers would end up throwing the remnant way out and not growing? It's possible, but the nature of the oligarchic growth that we're discussing here means that only the initial few mergers have the prospect of giving you significant kicks. Once you have your very massive guy running away, the mass ratio between it and the things it merges with is small, and therefore the kick is small. In addition, because it'll be accreting things from totally random directions, its spin will be low. This is also something which argues for relatively small kicks. In our particular case, if you have a velocity dispersion of 300 kilometers per second, typically the escape speed from the center is a few times that, so maybe 1,000. There will therefore only be unusual circumstances, bad luck if you will, that will lead to a kick strong enough to eject your growing object. So most of the time it should be able to stay where it is. So in summary, binary interactions in galactic centers could produce interesting sources for LIGO, the binary mergers, or LISA, where you have the emery produced by tidal separation. It might produce distinct tidal disruptions, and we've proposed, related to the lack of binaries, a new mechanism for the rapid production of massive, supermassive black hole seeds. Thank you.